4.2, what derivatives tell us, part 2, we're going to be talking about some kind of curve. And when things are some kind of turning point or something's happening at certain values. If we can look at this quick sketch, we are on an interval from A to B. It's an enclosed interval. And we can see that from this graph, we might here at C sub 1 have a horizontal tangent. C sub 2 has a horizontal tangent. C sub 3, C sub 4, and C sub 5. And then we've got the endpoints A and B. So I can see here that if I was to do some testing of positive and negative, increasing, decreasing of functions like we did in the first part, we may not always have something that's true, because in C sub 1, I have that there's no extrema. Yes, there was a horizontal tangent, but I was still an increasing function. So I have also that at C sub 2, I could have a local max there. It is a max. I went from increasing to decreasing. At C sub 3, I went from decreasing to increasing, so I did have a local min. At C sub 4, I have a horizontal tangent, but because of that corner or cusp, I'm not differentiable there, so I don't have an extrema there. I'm undefined. At C sub 5, I am just like at C sub 1, where I have a horizontal tangent, but I was a decreasing function, and I didn't really turn from increasing to decreasing or decreasing to increasing. So I don't have an extrema at that point. But if I notice, if I evaluate also the endpoints, A would be my absolute minimum. It is my absolute minimum of the entire piece of this interval. So I could look at what's happening at the endpoints as far as max and min points. So then I want to go ahead and I'm going to do something called the first derivative test. So it says here that the first derivative test is for a continuous function on an interval that contains some critical point C, and we're assuming it's differentiable. If the derivative has a sign change from positive to negative, we have a max at C, and if it's from negative to positive, we are a local min. And if it doesn't change at all, we have no local extreme value at that point, so we saw from the picture. Let's walk through something else here. We have a theorem, one local extremum implies absolute. So it's just saying on an interval, there's going to be at least one if I have something that it's implied, a change of sign from positive to negative slopes of the tangent lines from the derivative. So we're going to go ahead and try to do one. I have number 40. It's on this interval from -4 to 4. So when I want to go ahead and walk through number 40, the first thing I'm going to do is go ahead and take the derivative. And I'm going to set that equal to 0, and I'm going to solve. That's where I would have a critical point when it has a horizontal tangent. I solve for x, and I have a -1/2. So then I'm going to test on an interval where I have -1/2, and I'm going to evaluate at the endpoints also. So if I test by plugging in some interval value into the derivative, so I'm going to try plugging in a -1 for this interval, and I'm going to try plugging in a +1 on this interval and seeing what I get. I see my values are then really, I have a positive and a negative value, plugging it back into the derivative. So I do go a sign change from positive to negative, increasing to decreasing. I should have a max point here. But if I have it said I want to find what my critical points are. And then I want to go ahead and see if it's a local max or min. And it does show from the sign change we have a local max at x equals negative 1/2. But then I want to go ahead and in part C, I want to check for my values. And this is the step where I'm going to go ahead and evaluate back into the original function my critical point and my endpoints. I'm going to go ahead and evaluate and see which is then absolute max and mins. And if I do this, if I plug in negative 1/2, I have a 9/4. If I plug in negative 4 back into the function, I have negative 10. And if I plug in a positive 4, I have negative 18. So if this is the case, these are my values. This is my highest or most positive value on this interval, then this has to be my absolute max at that local max point. They're the same thing then. And then I have, if I'm looking for the entire interval, since it was closed, I'm looking for any other values that would be a minimum. And I see here that this is my lowest value. This has to be my absolute minimum. Then I have another example I want to go ahead and walk through because it has tangent in it. This is number 48, and we're going to go on the closed interval from -1 to 1. And then from here, I want to go ahead and take the derivative. And the derivative of my inverse tangent and my derivative of x cubed. And I'm going to set this derivative equal to 0 and solve. I should get on this one that you want to go ahead and solve for x, critical points, however you want to go about solving at this point. Make a common denominator. If you just want to multiply everything through by 1 plus x squared, and you get 1 minus 3x squared times 1 plus x squared equals 0, and go from there. I do see that I get a critical points of positive and negative 0.5135782. And then, yes, you can go probably a smaller decimal places than that I have here, but it's up to you. You want to go ahead and set up your test intervals. And then we should be able to test it. We see we go negative, positive, negative. And then you're going to want to go ahead and test at your endpoints also. So you're going to be evaluating it at 4 values into the original function. Remember, these were into the derivatives. I plugged in a -1. Into the derivative, I plugged in 0. And in this one, I plugged in a +1 to go ahead and see those sign changes. We're going to test concavity and inflection point. And what are those? Concavity is where it's a cupped or a slightly curved. We're definitely not a straight line. Concavity is talking about that curved shape. Is it cupped where the cup is facing down, or is the cup facing up? Concave up or concave down on an interval. And where we change concavity is what we call the inflection point. So from up to down or vice versa. So we can go up and then we can go down. And at that point that we change concavity is called the inflection point. So we want to test for concavity. And we're going to be taking the second derivative. And the second derivative, if it's positive on an interval, we say it's concave up. And if it's negative on an interval, we say it's concave down. If it did not change signs, there is no reflection point at that point that we've tested for. So that we have some point C. So what we're going to do is the same type of situation we've been doing with the first derivative test, where we're going to take the second derivative now, set it equal to 0, find some critical points, and we're going to do our interval testing for concavity. So we have, for example, it says sketch on the graph from -infinity to infinity, where the first derivative is negative. so we're decreasing. And the second derivative, or really think of that second derivative as the rate of change of the tangent lines to the function. It's the second derivative, so it's still rate of change, but we're doing it of the tangent lines. And the rate of change is decreasing. It is negative. And that's the case, we're going to be a concavity that's down. And it says from the interval from negative infinity to 0. So at 0, we're going to have some kind of change happening. The next line says the first derivative is less than 0, so we still have negative tangent lines, negative slopes, and then it also has a requirement that the second derivative is now positive or with a concavity that is up on the interval from 0 to infinity. So they want us to sketch one continuous graph that has all these requirements to it. If that's the case, I'm coming from negative infinity with some kind of negative tangent lines, and we're going to 0, and it was concave down. And then at 0, now I'm going to be concave up, but I still have a decreasing negative tangent lines. So in this case, the entire interval, or the entire graph, because they said to go from negative infinity to positive infinity, is continuously negative tangent lines, but we have concavity change from negative concave down to positive concave up. And that's how 55 would sketch. So if we're going to go ahead and test for concavity, let's try doing 57. And we're going to take the first derivative of this function, and then I have to take the derivative again. Find the second derivative, and I have 12x squared minus 12x. And this is what I'm going to set equal to 0, so I can look for inflection points and concavity. So if I do that, I'm going to factor out a GCF of 12x and have x minus 1 equals 0, and then I end up having x equals 0 and a positive 1. If I want to then go ahead and set up my interval testing, 0 and 1. Remember, you're plugging back into the second derivative, so I'm going to plug in a negative 1 back into the second derivative. Here, I'm going to plug in a positive 1/2. And my last interval here, I'm going to plug in a positive 2. When I did this, I checked for sign. Turns out this is positive, this was negative, and this was positive intervals. So I do change sign between each interval. I went from positive to negative, negative to positive. These are inflection points at this point. I can definitely call them inflection points. So I have inflection points at x equals 0 and 1. And then I want to know, where are the concavities happening? I can say that this graph is concave up, and I'll go from left to right, doing interval notation from negative infinity to 0. And we're going from 1 to positive infinity. It is where the intervals were positive, concave up. Concave down, where my interval was negative, is from 0 to 1. We're going to do the second derivative test for local extremas. Now we've done testing with first derivative for increasing, decreasing, and then we evaluated to try to find the local extremes, max and mins. But now we're going to go ahead and try to do the second derivative test. It says if you take the second derivative on an open interval containing some c, and the second derivative is positive, we have a local min. If it's negative, it's a local max. And if it's equal to 0, it's inconclusive, and you have to either check it more in detail what's happening. So it could be local max or min, or it could be neither, and you have to investigate further. So I'm going to go ahead and try to do number 79. So when we do this second derivative testing, we're going to take the second derivative, find the critical points, and but before I get there, they said, what's the critical? It says f prime of c. So what I'm really doing, and the key to remember second derivative testing, it's the first derivatives critical points plugged into the second derivative. All right, so let's try this. Number 79, I have the function x squared times e to the negative x. So my first step is I'm going to find the first derivative using product rule. And I'm going to set that equal to 0. When I set this equal to 0, I'm trying to solve, I have this issue of e to the negative x. I'm going to go ahead and factor that out. And actually, I could factor out an x also, but I think maybe I might do it differently like this and show you that all these factors, I have a 2 minus x is my last one. How do I find set e to the negative x set equal to 0? What factor would that cause it to be 0? And it nothing will. There is no value that would make this e to the negative x ever 0. I'm just going to go ahead and divide through by e to the negative x on both sides. So I'm now left with this value, and I can solve for x, and I get x equals 0 and 2. So I'm going to go ahead, and next step is I'm going to go ahead and find the second derivative. If I find the second derivative, which kind of gets messy on us, I should have 2e to the negative x minus 2x e to the negative x minus 2x e to the negative x minus x squared e to the negative x. Oh my goodness. If I went ahead and I left it like this, I could simplify it if you would like. We could have 2e to the negative x. I could have now negative 4x e to the negative x minus an x squared e to the negative x. From here, this is where I'm going to do my second derivative. I found the critical points that I'm going to plug into and evaluate the second derivative. So I'm going to plug into the second derivative 0, and I'm going to plug into the second derivative 2. In this case, I see that I have a 2 here, and when I did this one, I didn't even finish evaluating. I just found that it was a negative value because this is where I wanted to go ahead and try to find from here. I can see when I have this, I could keep going. I'm sorry. Let me keep going with this one. I have 2 over e squared minus 8 over e squared minus 4 over e squared. And if we keep going from there, I do have negative 10 over e squared. Okay, so I left it at this, and I just wanted to tell myself that it really is a negative value. I'm looking for my local max and min. And because of this, second derivative testing, I have this f double prime of 0 is equal to 2. This has got to be my min. And you may think, but it's the positive one. But let's go back and check from our second derivative testing. It said if the value here was positive, we have a local min. And then it said also if this value is negative, we have a local max. So this value was our positive one. It is a local min. And when we evaluated at x equals 2, we saw it was negative. This one is our local max. The last slide I have here is just a final summation that is in our textbook of all the different things we were doing in this section, what derivatives tell us. That we can see going from, when we have a differentiable curve, using the first derivative for increasing and decreasing, doing sign changes for local max and mins using first derivative, and then we also had second derivative for concavity inflection points.